Bismillahirrahmanirrahim. Welcome everyone. I'm Dr. Ambreen and I am physical therapist by profession. I'm delightful to be here on the platform of University of South Asia to tell you about pharmacokinetics. I've selected this topic as the request of the few students who want to revise the pharmacokinetics. I will be glad to answer any question that you may have at the end of this presentation. As this is the topic from the subject of pharmacology and therapeutics 1, you can say Introduction to Pharmacology for the students of nutrition. This is the subject for both the students of Doctor of Nutrition and Doctor of Physical Therapy, Semester 5. Firstly, I again like to revise the course introduction. Pharmacology is basically designed to allow the nutritionist and physiotherapist to build a comprehensive understanding of the principles of pharmacology. They must have an understanding of the characteristics and use of these drugs and to understand the drug interaction and the common medication profile they are going to come in contact with various prescriptions. Nutrition, wellness, and disease prevention are the areas of great interest in public. Rapid advances in the science have enabled much more detailed understanding of the nutrition in the recent years. And this course is basically for the beginners that is going to focus on how the macronutrients, micronutrients, or other factors that are going to affect the nutrition, such as the absorption, metabolism, nutrition for the life sciences, and nutrition therapy for the clients of various ages and with various illness is going to affect. This course will also describe how the physical therapy interventions like a thermal agent and soft tissue mobilization and exercises are going to affect the drug absorption and drug distribution. We must also be able to explain how the altered pharmacokinetics may alter the drug effects. Explain how this may be recognized in the patient receiving of physical therapy. Explain how an anti-inflammatory steroid will reach the supraspinal intestine following in the oral administration. And we have to explain how the absorption and distribution of insulin are altered by the exercise, thermal agents, and soft tissue mobilization that you are going to apply at the site of injection. We have objective to predict the possible issues that may be encountered by the person's history and the use of both prescribed and over-the-counter drugs. We must be able to recognize the potential problems that may occur during the session with the patient who may be using the prescribed and over-the-counter drugs. And you must, as student and a therapist and nutritionist, must be able to answer all the potential questions from the patient regarding the prescribed and over-the-counter drugs, and to develop the critical thought pattern and work with other members of healthcare team. This is very important to understand the pharmacology. And this course is actually from the subject of this subject is from different books. I have gathered this material from the books like the Pharmacology for Physiotherapy by Pathology Kumar, Pharmacology by Katzen, Pharmacology by Lippincott, and these are the main books from where I have collected all this material. Now coming towards the topic, what is pharmacology? Pharmacology is a science. Science of what? It's a science which deals with the actions of chemicals and they are going to act on the biological system. So this is the science that is going to deal with the action of the chemical on the biological system. The action of the chemical agents mean the actions of the drugs on the biological system, on the living organism. And medical pharmacology, we have defined it an area of pharmacology that is concerned with the use of chemicals. And why you are concerned with the use of chemicals? In order for the prevention, for the diagnosis, for the treatment of diseases, especially in human beings. So what is it? It is an area of pharmacology that is concerned with the use of chemicals and the prevention, diagnosis, treatment of the diseases, especially in human beings. We have divided all the pharmacology into two main branches. Number one is pharmacokinetics, the other one is pharmacodynamics. This is very important to understand these two branches of the pharmacology. One is pharmacokinetics and this is other one is pharmacodynamic. A person who is going to study pharmacology must have understanding of these general principles of pharmacokinetics and pharmacodynamics. Then he or she may be able to learn the use of the drugs in different applications and different conditions. So what is this pharmacokinetics and dynamics? When a prodrug or a drug given through any route means the route of drug administration. When a drug, a prodrug given through any route, if absorbed, it reaches to your systemic circulation. Or when it reaches to the systemic circulation, it is going to distribute to all the areas of the body. So when it is going to distribute, it is obviously going towards the target site, meaning the tissues you are going to required, and even where it is not required. Along with this distribution, a few of the portion of the drug is going to eliminate it, and how much the portion is going to be eliminated depends upon the every drug. So it varies to drug to drug, and all what is going all around is would be metabolism, and ultimately the drug has to excrete out of the body. And the whole this entry of the drug, its absorption, its distribution, its metabolism, its excretion, this is called pharmacokinetics. Okay, fine. This is pharmacokinetics. We said when a drug enters, it reaches the systemic circulation. From here we start. When it reaches the systemic circulation, when it reaches the target site, and where it acts at a site of action, it acts. So it produces few pharmacological effects. The pharmacological effects can be of two types: therapeutic or toxic effect. This is what is pharmacodynamics, the action of the drug on the site that can be either therapeutic, that can either toxic, and this is pharmacological action of the drug on the living tissue, the effects of the drug on the human being, on the body, on the tissue is called pharmacodynamics. Pharmacokinetic is what our body is doing with the drug. What a body can do, it can absorb, it can distribute, it can metabolize, it can excrete. What a drug can do, it may produce certain pharmacological action. That can be either therapeutic, that can be either, toxic effects. So I earlier use a word prodrug or a drug. What is a prodrug? It is also a drug, but it is inactive before metabolism, inactive in nature when it enters, but it becomes active after metabolism. So it is an inactive form of the drug that enters in the body, and after reaching in our like liver or stomach, it gets activated after metabolism. So its metabolites are basically active. While a normal drug is active by nature when it enters, it depends further how it is going to happen with that. Coming towards the pharmacodynamics, we said when a drug enters in the body, it's entering through different routes of administration. The routes of administration can be different, like you all know it can be oral, it can be rectal, it can be percutaneous, it can be intravascular, intravenous, intramuscular, intrathecal in the brain, and inhalational in the air, like airways. Fine. So what the drug that we take orally or rectally reaches to the gastrointestinal tract. The drug that we apply on the skin is going to reach to the blood vessels, to the systemic circulation, and the one that we apply intravenously directly reaches to the plasma, and the one that we apply intramuscularly, like through muscles, is it going to reach to the plasma, and the one intrathecally, like from the cerebrospinal fluid to the brain, it is going to reach to the plasma, and the one that we are taking through inhalation route, then it goes to our lungs, where airways, from here it is going to reach to the alveolar circulation, and it is going to reach to the plasma. And what is actually going to happen, all the drug is going towards the red rectangular area, that is your plasma, your systemic circulation. From here it again moves here and there, and this is called distribution. It moves towards all the areas of the body, this is called distribution. So the arrival of all the drugs to the plasma is called absorption. And after absorption, all the drug is going to distribute all over the body. Fine. Either it is required at a site, either it is not required. It travels with circulation all over the body. There is the mechanism that is going along with this, that is biotransformation. I'll tell you in the next coming slide. Right now I'm going to skip it. Okay, fine. The drug is actually distributing after metabolism. It is going to excrete out of the body, like the one that is from the kidney. It is going out through the urine. The one that is through the gut, it is going through feces. The one that is going to the breast and sweat glands is going to excrete out from the milk and sweat. And the one that is coming to the lungs is going to excrete out in the form of the expired air. So this is the summary of this entry and this distribution and excretion. So these are the excretory routes. the urine, feces, milk, sweat, and expired. There is another process of elimination of biotransmission. I'm going to skip it right now. I'll tell you in the end of this pharmacokinetics. Now coming towards the route of drug administration, let me tell you there are a number of the routes of drug administration like oral, and it can be inhaled, it can be oral, it can be parenteral. Parenteral means in the veins other than antral. It can be rectal, it can be transdermal, it can be topical, it can be IV intravenous. So there are the number of the routes, and all these routes have been categorized or divided into certain classes. So the possible route of administration are divided broadly into three classes: antral, parenteral, and topical. Antral means through the alimentary canal, like sublingual under the tongue, buccal, like here in the gum and the mucosal wall, oral that we take in the form of syrups and tablets, and rectal through the rectum. Coming towards this picture, you can see sublingual is the one that is you are going to place under the tongue. Fine. Buccal is the one that you are going to place between the gums and the mucosal cavity. And oral can be either in the form of tablets, it can be either in the form of like syrups. Rectal is in the form of, through rectum is in the form of suppositories that is being used for the patients of constipation. Coming towards the sublingual or buccal route, I would like to tell you all the drug that we take through sublingual route or buccal route directly enters to the systemic circulation. You can see in this picture there is a vessel, sublingual vessels, the veins that are present under the under the you can say the buccal cavity. What they are going to do is they are going to carry all this like drug directly into the superior vena cava. So the one that is going to be present in the sublingual cavity, it is actually going to penetrate the mucosal wall and directly going to reach towards the like venous circulation and going to reach towards the superior vena cava. You can see this and this. Then there is another term, first pass metabolism. We will discuss the first pass metabolism in detail. But right now, I just want to tell the drug that is going to the sublingual route does not enters the first pass metabolism. It avoids the first pass metabolism. So the total amount of the drug that is going to come in the sublingual or buccal cavity is actually going to your circulation. So it may have a 100% almost absorption because it is not going to face first pass metabolism. The point is, what is this first pass metabolism? It's the metabolism that is going to occur when the drug is going to is going to pass through different through liver, and it is going to have an incident which is called first pass metabolism. Coming towards the oral route, you can see when the drug is going to enter through the oral cavity, it is absorbed. Okay, fine. It reaches to the stomach, and after reaching to the stomach, it has to go towards the portal circulation. From the portal circulation, it has to enter into the inferior vena cava, and which we want to say it enters into systemic circulation. So what happens meanwhile when it is in the liver? In the liver and the stomach, there are certain digestive enzymes that may alter the composition of the drug, and in the liver there are certain microsomal and non-microsomal enzymes that actually breaks down the drug and convert it into inactive form somehow. And how much the drug is going to convert into inactive form, that depends upon drug to drug. So the amount of the drug that can be degraded or metabolized varies from drug to drug. So I can't say this drug, every drug has to go through metabolism like 50% or 60%, 80% metabolism. The metabolism, first pass metabolism that is going to occur in the liver depend from drug to drug, vary from drug to drug. So they are saying all the drugs that you are taking through the oral route is getting absorbed into the portal circulation and then into the systemic circulation in varying amounts, depending on the first pass metabolism. Now you can see in this picture the stomach and the mesenteric vessels, and they are covering all around the vessels, the intestine and the lower part of the stomach, and they're going to carry this whole metabolize all the substances from the stomach and intestine into the liver, and from liver it is going towards the inferior vena cava. Now coming towards the rectal route, the rectum actually have two blood supplies, two blood vessels that are actually taking away the blood from here. What they are, among one is directly leading towards the superior vena cava, the other one is going to enter into mesenteric vessels, and from mesenteric into the portal circulation, from portal into the inferior vena cava, while the other one is directly going to the inferior vena cava. So almost 50% is going directly into the systemic circulation, and remaining 50% is going into the portal circulation. So this is a summary of all these drugs that we are saying that they are going to from heart. Like you can see from the liver, they are going towards the inferior vena cava, and they are going to enter the systemic circulation. And from the muscles, it is going again into the superior vena cava, and inferior vena cava, it is going to enter in the circulation. All these drugs are going to enter into the systemic circulation. And you can see from the intravenous route, they are also going to enter in the systemic circulation. And from the transdermal route, the drug molecules are going into the systemic circulation. And after reaching the systemic circulation, they are going to be distributed all over the body. Fine. Intravenous, as 100% is going into the systemic circulation. So you are saying this, they does not faces first pass metabolism. Intramuscular, going almost 100% is systemic circulation. Transdermal, obviously under the skin there are blood vessels, but the drug is going variably into the systemic circulation. It has only option to reach into the systemic circulation, but depends upon the vessels or the composition of the drug, that how much it easily can cross the walls and different areas. And drugs that are going to take them through the inhalation route, the drugs mainly remain locally in the lung tissue and very little going into the systemic circulation. Fine. Now coming towards the main topic of the discussion, that is pharmacokinetics. What is pharmacokinetics? It is the study of the absorption of the drug, the distribution of the drug, the metabolism of the drug, and the excretion of the drug. There are four features of pharmacokinetics: absorption, distribution, metabolism, and excretion of the drug. Fine. What is pharmacodynamics? That will tell you it's very important. Pharmacokinetics and pharmacodynamics. Pharmacodynamics is where it acts. So where it acts would be the site of action, then how it acts would be the mechanism of action, and what are the effects are the pharmacological effects, like useful and adverse effects. Fine. So where it acts, how it acts, what are the effects, they are pharmacodynamic properties. Coming towards the first point of the pharmacokinetic, that is absorption. Pharmacokinetics is the study of the absorption of the drug, the distribution of the drug, the metabolism of the drug, and excretion of the drug. So absorption of the drug is the passage of the drug from the site of administration to the application to the blood circulation. This is called absorption of the drug. For a drug to reach to its site of action, it must pass through the various membrane depending upon the route of administration. So absorption occurs by one of the following process. It either has to pass through the passive diffusion, carrier-mediated diffusion, or facilitated diffusion, active transport, or through endocytosis. Like you can see in this picture, this is a normal structure of a cell membrane, that is a lipid bilayer. We all know. And the facilitated diffusion is the diffusion that is from high to low concentration, and but they need a facilitator or carrier that is going to carry the molecules from one side and going towards the other side. It does not go themselves. They need a carrier, a helper that is going to facilitate the diffusion. The next is active transport. It is against the concentration gradient, that from low concentration to high concentration. So it always requires energy, ATP, for like its migration from this place to another place, transformation. The next is endocytosis. Endocytosis is engulfment of the molecules by the membrane, and they are going to carry in the form of droplets to the next area. Let me explain the absorption. In order to explain the absorption, we must have to consider different factors of the absorption that can affect the absorption. There are a number of the factors that can affect absorption. Absorption is the first step of the pharmacokinetic. So what are the possible factors that can affect the absorption? That's disintegration and dissolution time. That's formulation. That's particle size, route of administration, lipid solubility, pH and ionization, area of vascularity of absorbing surface, gastrointestinal motility, presence of the food, metabolism, and disease. So today we are going to discuss these 11 steps of absorption in detail, how they are going to affect the level of absorption of a drug. Coming towards the first point, let me explain this point, that is disintegration and dissolution time. Disintegration is the breakdown of the product, the substance is smaller particle, and dissolution is going to mix into the fluids. The aqueous solutions are better absorbed. as compared to the oily solutions or suspensions or solid forms that are poorly absorbed. Why? Because the rate of dissolution, disintegration actually governs the rate of absorption. The next is formulation. What is formulation? Pharmaceutical formulation, actually the same drug that is manufactured by different pharmaceutical companies made different. Pharmaceutical preparation can be formulated to produce the desired absorption. Another substance is used with the drugs as diluent like anti and starch and lactose sometimes has been added into the compound. These are the inert substances. The reason of adding these inert substances in the drug is to interfere the absorption. So I just want to clear this point that different pharmaceutical companies are manufacturing the same amount of the drug and due to which their absorption may vary. And sometimes we intentionally have added some inert substances in it in order to interfere the absorption. There are certain sustained release preparations like dapper injections, multi-day tablets, and sustained release. Dapper injections are in the form of oily viscous, depending on the particle size. Multi-layer tablets mean the terracotta tablets. Sustained release capsules mean the resins-like substances that are going to be releases in the form of gradually going to release and going to have a slow and sustained effect. Coming towards the particle size. Particle size is very important in order to govern the rate of absorption. How? As the smaller the particle size, it would be more easier for the drug to get absorbed. So smaller particle size is important for the better absorption. Like the drugs like corticosteroids, digoxin, aspirin are better absorbed if given in a powdered form because they have a large particle size. They actually require the time to disintegrate and then to absorb. So what we do is in order to help the patient the absorption rate, we actually use them in the powdered form and make the particle size so small so that it would be more easier for the drug to get absorbed. The next point is lipid solubility. Let me explain this lipid solubility. Higher the lipid soluble drug would be, more will be the absorption because the membrane through which it has to absorb are actually made of phospholipids of the cell membrane. So if a drug is highly lipid soluble, it will be more and rapidly being absorbed. Fine. Lower would be the lipid solubility, more difficult for the drug to cross to the membrane. Coming towards the next point, route of administration. Route of administration means through which route we are going to administer the drug. So for example, if I'm going to take a drug through the parenteral route, like intravenous, intramuscular route, the drug is directly reaching the systemic circulation, meaning it is 100% is going to absorb and it is immediately going to start its action after distribution. But a drug that has taken through the oral route, it reaches to the stomach and then from the stomach circulation, it is going to enter the portal circulation. From portal, it reaches to the systemic circulation. So it has to cover a long route to reach to the systemic circulation, and it has even to face a number of the enzymes, a number of the like you can say particles that may degrade their like presence. The next is pH and ionization. It's very important because pH and ionization are the important features that are going to affect the absorption. How? If the drug is unionized, means it's not break down, it does not become an ionic component, it's better absorbed. But if drug is ionized, it's poorly absorbed. Degree of ionization is going to go on the degree of absorption of the drugs. The next is pH. As we know, the medium of the stomach is acidic. Fine. If I am going to take a drug that is basic in nature, what it is going to do is, when it comes to the acidic medium of my stomach, it will get ionized, obviously. And we earlier said if a drug gets ionized, it will not be absorbed. If a drug is ionized, it will not get absorbed. For this, I'm saying if I take an acidic drug, it reaches to my stomach, it is going to like not going to ionize, so it is going to absorb. So the problem is for those drugs that are ionic, that are basic in nature, that has to pass through the stomach and then reach towards the intestine that is in basic in medium. So such drugs are actually protected by using the terracotta tablets. They are given an extra layer in order to prevent the stomach environment and that area so that they may pass to the stomach and reach the area where they can be absorbed. So they can be better absorbed in the alkaline medium that is basically our intestines. There are certain examples that you have to keep in your mind for the MCQ point if you have further like. Coming towards the area and the vascularity of the absorbing surface, larger the surface area, more would be the absorption. Like in the case of angina, local blood flow, higher the blood flow of that area, more the drug is going to reach towards the leg in the systemic circulation. The next is gastrointestinal motility. This is very important. The rate of gastric emptying is also like governing the rate of absorption. If the gastric emptying mean staying in the stomach is less, the passage of the drug to intestine is quicker. If the passage of the drug to the intestine is quicker, mean it will have more time to stay in the intestine, and intestine is a highly vascular area and a highly large surface area. So what is going to happen? Drug absorption would be faster. Fine. So if in case of diarrhea, due to increased GIT motility, due to increased intestinal motility, there is less time available for the drug to stay in the intestine, due to which their absorption has been reduced. Presence and the type of the food. They are aspirin, tetracycline, they are poorly absorbed in the presence of the food. So drug form complexes with the food constituent, and such complexes are poorly absorbed. Certain drugs like ampicillin, erythromycin, rifampicin are well absorbed on or empty stomach. In case of metabolism, extensive metabolism of the drug while passing through the GIT and portal circulation, leading to decreased absorption. Nitroglycerin and insulin are the drugs that are going to face high metabolism. Diseases. Diseases of the gut like malabsorption results in reduced absorption of the drugs. Coming towards the next topic of this pharmacokinetics, that is bioavailability. I do love this topic, this term bioavailability, what it is. Bioavailability comes after first pass metabolism. For this, we have to know about the first pass metabolism. First pass metabolism is the metabolism of the drug during its first passage from the site of absorption to the systemic circulation. It's also called pre-systemic metabolism, first pass effect. It is one of the important features of the oral route of the drug administration. What it is, it's metabolism of the drug during its first passage from the site of administration, absorption to the systemic circulation. For a drug that you are going to take through the oral route, it reaches the portal circulation. For portal circulation, meaning it is going to enter the liver. Liver is one of the major metabolic site where both the metabolized and unmetabolized drugs enter into the systemic circulation, and if the drug is going to come through other area, it also reaches the systemic circulation directly. It doesn't face the passage to the liver, so it does not get metabolized. Now, in short, unmetabolized fraction of the drug which enters the systemic circulation is your bioavailability. Bioavailability. Fine. What it is, it's bioavailability. Okay. And what is it? We're going to define it in proper term as a fraction or a percentage of what? Of the administered dose of a drug, which reaches to the systemic circulation, but in unchanged form when given through any route is bioavailability. The complete definition is fraction or percentage of administered dose of the drug which reaches to the systemic circulation in unchanged form when taken through any route is called bioavailability. There are the number of the factors that can affect the bioavailability, like absorption. Those that affect the absorption also affect the bioavailability. So after a drug taken through oral route, there is altered absorption. There are a number of the factors like portal circulation, liver, first pass effect, and the amount of the drug that remains unchanged is your bioavailability. If more drug is going to pass through this first pass effect, there will be less amount that is unchanged, then there would be less bioavailability, less amount of the drug in the systemic circulation. So how can you prevent your drug from first pass metabolism? Usually the route is changed for the drugs. It's very low bioavailability due to first pass effect, or either due to decreased absorption. Dose is increased according to the required therapeutic concentration. The next is power entry route is really needed for the drugs which have 100% bioavailability after the oral intake. So those factors that are going to affect the absorption are going to affect the bioavailability. So the extent of absorption, the rate of absorption, first pass effect, they're all going to affect the bioavailability. Now there poses a question how first pass effect can be avoided. It can be avoided. How? By changing the route of administration. For the nitroglycerin, you are going to give it sublingually instead of giving it orally. Or adding an enzyme inhibitor, like you are going to add up carbidopa with levodopa. we are going to increase the dose like propranolol in case of propranolol. Then next coming towards the second most property of pharmacodynamic, that is distribution of the drug. So after absorption, there comes the distribution of the drug. What is this? We said when the drug reaches to the systemic circulation, it gets distributed to the various tissues of the body. Fine. So when a drug gets distributed, it means after a drug reaches to the systemic circulation, it gets distributed to other tissues. Unionized liposoluble drugs are widely distributed throughout the body. A rate of distribution depends upon the site of administration, dosage form, the rate of gastric emptying, controlled release population. All these are the factors that are going to affect absorption. The drug, after for distribution, reaches to the regional like systemic circulation, and from the other side of administration, it reaches the systemic circulation. And after reaching to the systemic circulation, it gets distributed. Where? The site of action, the liver, to the kidney, and different sites of the body. So the thing that you can see in the circle, the drug usually binds with the plasma protein. This is a very important thing. What is the relationship of drug with the plasma protein that we will discuss in detail. Right now you are just going to look the drug and the plasma proteins may bind to each other. Fine? So we will discuss this later on. The drugs are being distributed to vascular compartments. Drugs are distributing towards the site of action. It is going to distribute it where it is even not required, and even it is being stored, it is being treated, it is being metabolized. All the processes are going along with all along. So technically, distribution is after reabsorption. The reversible movement of the drug molecules to various body compartments by permitting through various body tissues is called this distribution. There are certain barriers that are going to affect this distribution, like the cell membrane of various tissues. It prevents the transcellular movement of the free drugs, like smaller size ionized drugs which are liposoluble can easily be distributed. Special barriers that are going to be faced are placenta and blood-brain barrier. The drugs may enter all the body tissues, including the fetus of a pregnant woman. It may have to go through the diffusion membrane. It may pass through the facilitated diffusion, that it may be due to endocytosis. There are different compartments of the drug distribution in our body that are going to govern the rate of distribution. Coming to a special type of the pores in the capillaries of certain organs. The pores in the capillaries of some organs have specialized characteristics to meet the peculiar needs of the organs. Some of these characteristics are as follows. This is a picture to show you a comparison between the normal blood vessels and the blood vessels in the brain. The normal blood vessels, you can see there are the pores from where the drug molecules can come and go out. While the blood vessels that are present in the brain, they are surrounded by the glial cells that are going to act as a barriers. So these glial cells are going to protect the cells, and further there are tight junctions and no pores like the normal blood vessels. So you can compare these blood vessels with the normal blood vessels. Why Allah subhanahu wa ta'ala has made these blood vessels so different? Because Allah ta'ala wants to protect these blood vessels or these brain tissues from the particles that are moving in the circulation. So Allah ta'ala does not want to get out these particles out of the vessel and to reach and give harm to the brain tissues. So in order to by nature, in order to protect it, the protective response, the protective mechanism in our cells or in our blood vessel they are having tight junction and they are protected by the glial brain cells. Here, I want to explain you the nature of the blood vessels, and on the basis of the anatomy or the structure of the blood vessels, you may be able to understand how the particles or how the substances can move in and out of the blood vessel. So there are three types of the blood vessels: continuous, fenestrated, and sinusoidal blood vessels. You can see in sinusoidal blood vessels there are large pores. In fenestrated blood vessels there are small pores, and in the continuous blood vessels there are very less pores. So in the brain, junction between the capillaries and endothelial cells are mainly the tight junctions, and that allows only extremely small molecules such as water, oxygen, carbon dioxide to pass in and out of the tissue. While in the liver, the opposite is true. The clasps between the capillary endothelial cells are wide open. So you can see in this picture, they are wide open. Purpose of being wide open is so that almost all the dissolved substances of the plasma, including the plasma proteins, can pass from the blood into the liver. While the pores of the intestinal capillaries are midway between those of the muscles and those of the liver, while in the kidney, there are the many small oval windows called fenestraries that penetrate all the way through the middle of the endothelial cell. So that the tremendous amount, so many amount of like small molecular ionic components can filter through these glomerular cells. Coming towards the blood-brain barrier. What is this? This is a barrier that is not fully formed at birth. It consists of tight junctions of endothelial cells of the capillaries and glial cells surround these endothelial cells, and they are going to protect the brain from the foreign substances in the blood that may enter the brain. They protect the brain from the hormones and neurotransmitters in the rest of the body. They maintain a good, constant environment for the brain. Similarly, there are placental barriers. They are the barriers that allows the lipid-soluble unionized molecules only. Water soluble and the large molecules size they can't cross the barrier. So the lipid insoluble can only cross to less extent. What is this? Placental barriers only allow the lipid soluble unionized drugs. It does allow water soluble and highly molecular particles to pass through it. So the drugs that are taken by mother can give you several unwanted effects to fetus. So mothers, when they are pregnant, they must consider that this drug can even harm to their baby, so they must avoid these drugs. The process of distribution of the drug in the vascular compartment is in both free form and in the bound form with the plasma protein. So coming towards the point I was earlier, so you're going to say the blood, in the blood, the drug is going to have some relationship with the plasma protein. What it is, on reaching the circulation, most drugs bind to the plasma protein. The acidic one binds to albumin, the basic one binds to alpha acid glycoprotein. The free and the unbound fraction of the drug is only for available for the action and metabolism excretion. The free, the drug that is free, that has not made any relationship with the plasma protein, that is unbound, is only available for the action, for the metabolism, for the excretion. So it is only available for the pharmacokinetic and pharmacodynamic properties, but the one that has binding to the plasma proteins is not available for the pharmacokinetic, is not available for the pharmacodynamic properties. So the binding is usually reversible. This is important. If the binding is permanent, it's very difficult for the drug to work. This is usually reversible. The fraction of the drug binding is determined by the degree drug concentration, the affinity, the number of the binding sites available for the drug. So extent of the protein binding varies with each drug. Like warfarin is 99% plasma protein, morphine is 35% plasma protein binding capability, ethosuximab and lithium never bind to any plasma protein. So you can see the graph, the free drugs are always valuable for action while the bounded ones are stored and they are going to act as a reservoir in our body. Because they are not being utilized, they are not being utilized for any pharmacological action, they are not being excreted, they are not being metabolized. So an equilibrium is always present between the free and bound form. So when the concentration of the free part is reduced, how it is reduced? Due to elimination. It dissociates from the freedom. For example, I said warfarin is 99% plasma protein, 1% is free form. But when 1% of this free form has been utilized, the 99% 1% again comes and degrades and become unbound and it again available for the effects. The bounded fraction is not available for thermodynamic and kinetic processes. Free versus bounded fraction of each drug is generally constant. Warfarin is 99% bound. Drugs which have a high plasma protein may have long duration fraction. Obviously, they have a longer half-life. This is important. The drugs that have a binding capability are going to act for more longer time, long duration of action, longer half-life. There are certain examples of these drugs. Now, I'll let you explain this clinical importance of the protein binding. These drugs are very important clinically because when two drugs are given together, they start competition. And the one which have a highly plasma protein capability will remain binding to the drug plasma proteins, and the one which have a less protein binding capability will be dissociated and has to come in the free form, and due to which its amount, its duration of action can be reduced. Let's take example. The extent of protein binding, if changed, may lead to increase and decrease effect. Like extensive protein binding slows the drug metabolism excretion by glomerular filtration. How they are clinically significant? Because the free form is available for action, the bound form is acting as a reservoir, prolonging the duration of action. Coming towards the patient who is having hypoalbuminemia. Albuminemia is hypo means less albumin level in the blood. If there is less albumin level in the blood, there is no one who can bind with the drug. There is no albumin protein to bind with the drugs, as a result of which the binding size has been reduced, so the free fraction is increased. The plasma protein quantity, the chemistry is changed during these diseases, so it may increase or decrease the binding sites, and they may increase or decrease the free drug effects. Now comes the point of the competition between the two drugs. So drugs can even compete. I can say, for example, if the drugs are given salicylates and sulfonylureas are going to combine together. Salicylate displaces sulfonylurea. Sulfonylureas are oral hypoglycemic drugs. Methotrexate is the immunosuppressant. So they may displace these drugs, and salicylates may start protein binding, while the sulfonylureas and methotrexates are in the free form, they have to act. Indomethacin and phenytoin displaces warfarin. They are more stronger and more affinity with the plasma protein, so they bind and displace the warfarin. Sulfonamide and vitamin K displaces bilirubin, so due to which we can use this in connections in the neonates. Thus, the competition between the drugs are going to affect the increase, the free fraction is going to affect the level of the drug, its protein binding. Now, let me tell you a definition named as volume of distribution. It's the ratio between the drug administration in the body and the concentration of the drug in the plasma. So we also say it is the approximate the apparent volume of body compartments that is required to accommodate the drug in the same concentration as in the plasma. For example, if a patient is of 70 kg, the plasma volume is 3 liters and blood volume is 5 liters, extracellular fluid is about 12 to 14 liters, what is going to happen? Total amount of water is 40 to 42 liters. And for this purpose, we are going to, for this person, we are going to calculate the volume of distribution. As we know, it is amount of the drug in the body to the concentration of the drug in the plasma, in the blood. So let's take this example. This is the whole person. With this gray one is the extravascular compartment, the pink one is vascular compartment, and total units that are of the drug are 20. The amount of the drug is 20. 18 are present in the extravascular compartment, 2 are present in the vascular compartment. So the volume of distribution of this drug would be amount of the drug, that is 20 divided by the 2, that is concentration of the drug in the blood. So volume distribution is 10. If there is more like drug in the vascular compartment, then it would be 20 by 18, that will say volume distribution is 1.1. Similarly, we have taken example of 200 units and 198 are present in the extravascular spaces and lesser amount present in the vascular compartment. So if the drug concentration in the vascular compartment is less, volume distribution is obviously more, because they are indirectly proportional to each other. So volume distribution is low when a high percentage of drug is bound to the plasma protein. Thus, higher the volume distribution, higher will be the plasma, and vice versa. Coming towards the next property that is very important, that is redistribution. Redistribution is when highly liposoluble drugs are given through intravenous or inhalation route. They gradually distribute into highly perfused tissues in our body, that are basically brain and heart. They first prefer to move towards the highly perfusion areas, that is heart and brain and kidney. But sooner or later, they are going to redistribute it from heart, brain, and these tissues, less vascular tissues like muscles and fat. So this property is going to term as the redistribution. The drug initially goes to somewhere else. From there, then it becomes detaches and becomes to enter to the less vascular area. So early entrance, rapid exit, like in brain. Easy entrance, very slow exit. Other tissue flow dependent, that is slow exit. This is the last term of this topic, that is elimination. Elimination and excretion. Elimination is the chemical change in the drug molecule to have its pharmacologically inactive from the body. There are certain drugs that many of these drugs produce responses by themselves or due to their active metabolites, and the characteristics which are essential for absorption are unchanged through the process of biotransformation. Now there is a very interesting topic, that is biotransformation. What it is? It is the biochemical, the metabolic change in the drug molecule by the enzymatic processes to make it more excretable. You can see in this picture, I'll explain the process of biotransformation in our coming session. I just want to end up this session for this certain time, and inshallah I'll continue this biotransformation in the coming part or the coming lecture. Till then, Allah Hafiz. There's a message for you: stay home and stay safe. Allah Hafiz.